Good luck.
Okay. Hello, we are Doyeon Kim, Hyungwon An, Han, and Hyunjun Jo, and we researched about the curve optimization using curvature-based models with calculus of variations. So our research goal is to find the time optimizing train curve which connects two parallel straight railroads. To do so, we use the methods of differential geometry and calculus of variations and numerical methods of differential equations. So our motivation is the arc line model, which is composed of 2-point symmetric circular arcs and straight lines. In this case, the travel time is minimized when there are only two circular arcs. These are some theoretical backgrounds. We use the curvature and the Euler-Poisson equation, which is the method of calculus of variations. And we developed some speed formulas, and from the centrifugal force, we get the first basic formula, and to prevent the curve to curve so sharply, we induce the factor b, and to represent the real maximum speed Vmax of the train, we set the first formula, and this was actually used in our numerical analysis.
We calculated the time by using the following functional, as you can see above, and we conjectured that an odd curve, so a point symmetry curve, will have optimal properties in time. So we use the property called odd-even decomposition. So any function can be decomposed into the sum of an odd function and an even function, FO and FE. And so we conjectured and proved the symmetry theorem. So the theorem states that if a function f satisfies all these boundary conditions, then the time when using f is greater than or equal to time when using only the odd parts of f. And equality holds if and only if f equals fo. So we can minimize time when we use the odd parts of a function. So using odd functions will be optimal. And these are some methods for the proof. So we use the ideas from calculus of variations, and we use integration by parts and polynomial approximation to make our formula simple. And then we generalize the proof to C2 functions from polynomial functions.
So with aid of symmetry theorem, we can decompose our train curve, which is our situations, into 2-point symmetric curves. This makes our problem more easier. So to do the numerical analysis, we tried two kind of ways. First one is using calculus of variations, and second one is using polynomial approximations. So in calculus of variations, we use the adjusted speed formula, and to make the differentiability, we use the term using scalar instead of using absolute value. So we applied it to the Euler-Poisson equations, and we can obtain a boundary value problem which the optimal curve must satisfy. And we solved that BBP by using the BBP solver from the MATLAB, and we could get any solution curve from any given initial conditions. We also tried polynomial approximations, and we used the following polynomial P, which is satisfying following conditions and whose degree is lesser than or equal to 9. We used the following speed formula, and using loop in MATLAB, we could determine the coefficient of P, A2, A3, A4, which minimizes the total travel time.
We applied our optimal train curves to some real-world situations. So these are two situations in our country, South Korea, and we applied it to one subway line and a high-speed railway track. And we showed that our optimal curve in pink could minimize time by 10 to 20%. So conclusively, we calculated the formula for the maximum speed at a point of a curve that depends on the curvature of that point. And we conjectured and proved the symmetry theorem. So a point symmetric curve minimizes travel time, and we can show the similar results for the length of the curve. So we used this theorem to decompose our problem situation, and we applied calculus of variations and polynomial approximation to calculate optimal train curves. We are also planning to extend the results through 3D curves and develop algorithms that will determine the whole subway or train line. Thank you for listening to our presentation.